Hello everyone and welcome to the last video lecture for Math A37. The topic for today is power series. So far in the previous lectures we've talked a lot about series, which again is just the infinite sum of numbers, and we've talked about convergence and tests to determine if there's convergence or divergence for series. Let me get straight into the definition for power series. So definition. Okay, suppose we have a sequence, AK, be a sequence, and suppose we have some variable, x, and let x be a variable. So a power series centered at 0, power series centered at 0 is a series of the form starting at k equals 0 to infinity of ak x to the k. And we say that ak is, we refer to ak as the kth coefficient of the power series. The kth coefficient of the power series. Right, so briefly explaining this definition, a power series, well to begin, a power series has a centered. This is a power series that's centered at 0. Later in this lecture, I'll explain what it means for a power series to be centered at some other point, but if a power series is centered at 0, it's of the form ak x to the k. And this is different from a regular series because we have that variable x with the power k, right? That's where the word power series comes from. Now, since there's a variable x involved, in the same way that a function f of x takes on different values at different x's, a power series can, converge, diverge, or converge to different values for different x's. So let's define what it means for a power series to converge. So definition. Suppose we have a power series centered at x, so let ak x to the k, starting at k equals 0 to infinity, be a power series centered at 0. Centered at 0, right? Then we say that the power series, converges, at x equals c if the series ak times c to the k from k equals 0 to infinity converges. Right. So we're fixing x equals c, and then we reduce the power series into just a regular series, because now ak c to the k is just a constant for each k, so we can think of ak c times c to the power of k as just a sequence, and then this becomes a series. And now if the series converges based on the definition we've been working with so far, then we say that the power series converges at x equals c. And similarly, we can say that the power series diverges at c if the regular series ak times c to the k from k equals 0 to infinity diverges. Right, and we can also extend this definition to a power series absolutely converges at c, or conditionally converges at c, and so on. Right. So now the question we want to answer is, for what points x does a particular power series centered at 0 converge? So ak x to the k equals 0 to infinity converge or diverge, right? So the first point let's consider the simplest point, which is x equals 0. Um, so consider x equals 0. Right? So to determine if a power series converges at x equals 0, looking at the definition, we need to plug in the value 0 for x and then see if the series we get converges. So what happens when we plug in the value 0? Well, we get ak times 0 to the k. K equals 0 to infinity. And 0 to the power of anything is just 0 times ak is again just 0. So we get the series k equals 0 to infinity of 0. Right? And of course, the sum of infinite zeros is just 0. If you want to be more formal, you can also say this is equal to the limit of, as n goes to infinity, of the partial sums, Sn, which in this case is just 0 plus 0, which is equal to 0. So the limit of 0 as n approaches infinity is just 0. Right? Right. So since the limit of the partial sums exists, that implies that this series here converges, and therefore the power series ak x to the k, from k equals 0 to infinity, converges at x equals 0. Right? Which means that all power series converge at the point 0. It doesn't matter what ak is. AK could be any sequence of numbers, but every power series converges at 0. And of course, that's not that's not very interesting. We want to see, well, what other points does the power series converge at? So all power series converge at 0, but let's see some examples for, when can we figure out other points that the power series converges for. So the first example we're going to look at is example. So let's consider the power series 1 over k times x to the k. K starting at 0 to infinity. And the question is what points x does the power series converge? And this is a power series centered at 0. Series converge. Right. So in this case, the sequence a k is equal to 1 over k. Right. That's the sequence that defines the coefficients for the power series. And well, right again, just from the last slide, we know that it converges at x equals 0, because again, all power series do. Now let's consider the points not 0. So let's consider x not equal to 0. Well, since x is not equal to 0, and we can see from our power series, that implies that 1 over k times x to the k is not equal to 0, right? Because 1 over k is not 0 and x to the k is not 0. And since we have a series with, for a fixed x, so let me just write that down. For fixed x, we have a series with non-zero terms. Series with non-zero terms. Right? So therefore, we can use the ratio test for absolute convergence that we saw last time. So we can use a ratio test. Right, so to use ratio test, let's just say that bk, just to make things simpler, bk equal to 1 over k x to the k, right? So we want to use ratio test for non-zero x, so we need to consider the limit, consider the limit as k goes to infinity of bk plus 1 over bk, all of that absolute value. right? And this, of course, if I just plug it in, is equal to the limit as k goes to infinity of 1 over k plus 1 times x to the k plus 1 over 1 over k x to the k. Again, all of that in the absolute values. Right, and I'm going to simplify this to get limit as k goes to infinity. So the first fraction part becomes k over k plus 1, and then x to the k plus 1 over x to the k is just x, absolute value, x. Right. And again, I just want to point out that x is not equal to 0 in this case. And if we evaluate the limit k over k plus 1 as k goes to infinity, that's just equal to 1. And the absolute x as k goes to infinity is just x. So in this case, we just get 1 times x. Right? So now by ratio test, if the limit is less than 1, so if limit of, again, bk plus 1 over bk is less than 1, again, strictly less than 1, then we know that the series converges absolutely, so then series converges absolutely. Right, and the limit as bk plus 1 over bk is just equal to 1 times, 1 times x. Did I make that mistake here too? And this is less than 1 if x is less than 1. Sorry, absolute x is less than 1. So therefore, the series k equals 0 to infinity, ak, should be 1 over k, x to the k, converges for all x such that absolute x is less than 1, which is just equal to for all x in minus 1 to 1. Right? And also by ratio test, we know that if it's strictly greater than ratio test, the series diverges if the limit as bk plus 1 over bk, which is equal to 1 times x, is greater than 1. Right? So we know it absolutely converges, it should be absolutely converges, which of course implies converges. So it absolutely converges if the limit is less than 1, strictly less than 1, and it diverges if the limit is strictly greater than 1. So therefore, the power series, again, this implies that x is greater than 1. So the power series 1 over k, x to the k, diverges for all x. Again, the absolute value of x is greater than 1, so we have the interval minus infinity to 1, union 1 to infinity. Right, so it absolutely converges for all points in the interval minus 1 to 1, and it diverges for all points in minus infinity to 1, minus 1, union 1 to infinity. Right? But what about the point when absolute x is equal to 1? Right? The ratio test says that the theorem for the ratio test says that the ratio test is unconclusive, so we need to check those points manually. Right, so what about absolute x equal to 1, i.e. x equals 1 or x equals minus 1. Right, so the x equals 1 case, the power series is just 1 over k. I'm going to plug in 1, so I just get, times 1 from k equals 0 to infinity, which, I mean, that's just equal to 1 over k. 1 over k. Right, and you should be very familiar with this series at this point. This is the harmonic series, and we know from past lectures and the P series test that the harmonic series diverges by P series test. Okay, so therefore the power series diverges at x equals 1. At x equals 1. And now what about x equals minus 1? Well, then the power series, if I plug in minus 1, I get minus 1 to the k. K equals 0 to infinity. Which is equal to, I mean, this is the alternating harmonic series. Alternating harmonic series. Right. And if you saw the last lecture on alternating harmonic series, on just alternating series, we actually showed that the alternating harmonic series converges. This converges by the alternating series test, right? And again, I'm going to refer to the last lecture. See video. But this implies that the power series converges at x equals minus 1. Right. So let's put all those things together. So therefore, the power series 1 over k, x to the k, from k equals 0, converges. So going back, it converges at minus 1, and it converges in the interval minus 1 to 1, open interval. So it converges on the interval closed minus 1 and open 1. And it diverges, right, so this is x, and it diverges for x in minus infinity to minus 1, not including the minus 1, union, this time we're including the 1, to infinity, right, because it diverges at 1 and that interval. Now one thing that you may have observed is when we applied the ratio test here, we got that over here, we got that, either the limit, which is going to be absolute x times something, is going to be, it's going to be less than 1, or it's going to be greater than 1. Actually, let me write this down. So suppose we have like a generic power series, ak, xk, right, and we apply ratio test to non-zero terms, so for x equals 0, x not equal to 0, and let's assume ak is not equal to 0 because we want to apply the ratio test. This is just for to motivate the next definition. So we're going to apply the ratio test, and we're going to see that the limit as k goes to infinity of ak plus 1 over x to the k plus 1 ak x to the k. Right, if this is less than 1, then power series converges. converges. Right. Well, if I simplify this a bit, I get that this is equal to a limit as k goes to infinity of ak plus 1 over ak times x to the k, right? And this has to be less than 1. And let's suppose that limit exists. It exists and equals L. So this is equal to L times x, it's not x to the k, sorry, just x here, times x is less than 1, which implies that this power series converges for x less than 1 over L, which I'm going to call to R. Right, so for these values of x, the power series, then power series converges. Right. And in this case, we call R the radius of convergence. Right. And now notice that if L was equal to, the limit L was equal to 0, then for all x, the ratio test will tell you that this power series converges. And if the limit was infinite, well then, it diverges for all values of x. So let me compile that into a formal definition. So definition, suppose we have a power series centered at 0. Would be power series centered at 0. Right. So three things can happen if power series converges only at x equals 0, because remember all power series have to converge at 0. Then we say the radius of convergence R, we usually denote radius of convergence R, is equal to 0. And we say that the interval of convergence is trivial, or just the 0 set, set with just 0 in it. Right. Okay, number 2. It's possible for the power series, so if the power series converges everywhere, right, then we say that the radius of convergence R is equal to infinity, right? And we say that the interval of convergence is R, or minus infinity to infinity. Okay. And finally, number 3, if power series converges for x in minus R to R and diverges on x from minus infinity to minus R, union R to infinity, then we say that the value R is the radius of convergence. radius of convergence, and minus r to r is the interval of convergence, because x in that interval is where it converges. Interval of convergence. And in this case, the one important, very important remark is that the series, the power series, may or may not converge. Series may or may not converge for x equal to r, right? So going back, if I just go back to our example that we did before, this one, we see that the radius of convergence is 1 because the power series converges from the open interval -1 to 1, but it diverges from the interval minus infinity to -1 and then 1 to infinity. And on the points -1 or 1, well, it converges on -1 and it diverges on +1, right? So in this case, radius of convergence equals 1. Okay, so now that we've talked about power series centered at 0 and their associated radius of convergence and what their interval of convergence is, let's define what a power series is that's not centered at 0. So definition, a power series centered at some point x equals x naught is a series of the form AK, where again AK is just a sequence of numbers, x minus x naught to the k, right? So we replace the x with x minus x naught. And again, if if x naught equals 0, then we get our previous definition, right? So again, AK is sequence and x is a variable. Right. And again, AK is, we call AK the kth coefficient of the power series. So this is what it means for a power series to be centered at x equals x naught. Oftentimes, if you hear, if you're reading a textbook or, you see the question, suppose you have a power series and it doesn't specify the center. By convention, we assume that the center is 0, but in this course, always specify what the center is, even if the center is 0. Make sure you specify that a power series centered at 0, or a power series centered at some other point, x naught or whatever. Right. Now the thing that's different here is we saw that a power series centered at 0 always converges at 0. Well, in this case, if we apply the same logic, this power series always converges at x naught because x minus x naught is 0, so all the terms become 0. So I'm going to redefine the radius of convergence for a power series that's not centered at 0. So definition, let's suppose we have a power series centered at x naught. Centered at x naught, then 1. Yeah, if it only converges at x equals x naught, then radius of convergence is 0, and the interval is just the single point x naught. Right, 2, if it converges everywhere, then radius of convergence is infinity. And interval of convergence is just R. Okay, and finally, if the power series converges for x in x naught minus R to x naught plus R, and diverges for x in minus infinity to x naught minus R, union x naught plus R to infinity, then we say R is the radius of convergence. And again, you can very easily show that this is, if there's convergence at some points and divergence at other points, then it's going to be of this form. So then we say R is radius of convergence. Right, and the interval of convergence is interval of convergence is x naught minus R to x naught plus R. Okay, so if there is a finite interval of convergence as opposed to converging everywhere or converging just at a single point, then it's going to converge a distance R away from the point x naught. Right, so if I draw the three cases, if this is the real number line here, this is the point 0, and this is the center x naught, then either it converges, or let me make green converges. So it converges at the point x naught, but diverges everywhere. Right, so if red is a divergence, green is convergence, then this converges only at x equals x naught. And again, we're talking about the power series, a power series centered at x naught. Right. Or the second case is, again, if we have a power number line, then it's possible for the power series to converge everywhere. Right, so this one converges everywhere. Everywhere. And finally, if we have, again, the number line, then it's possible for it to converge only on some interval here, right? And this distance here is R, right? And it converges everywhere else. Diverges everywhere else, right? So this is a finite radius of convergence. R. And an important note is it may or may not converge at these points. So you have to check that manually. May or may not converge at x equals x naught minus R or x naught plus r. All right, so let's see one more example. Let's consider the power series centered at 1. That's given by 1 over k factorial times, x minus 1, for example. And k equals 0 is the starting point, and infinity is the ending point, of course. The question is, what is the radius of convergence? Right? That's just what is the radius of convergence? Right, so again, it converges at its center. So converges at x equals 1. Just a reminder that the center is x. It's x minus x naught. So in this case, x naught is equal to 1. So x naught is equal to 1. Right. So now let's consider the other points. X naught not equal to 1, i.e. 1 over k factorial x minus 1 is not equal to 0. So we can apply, so we can use the ratio test again. Ratio test. Again, this is for points x not equal to 1. Oops, sorry, not x not equal to. X not equal to 1. Right, so the ratio test tells us that we need to consider the limit as k goes to infinity of 1 over k plus 1 factorial times x to the k plus 1 over 1 over k factorial x to the k. Right, simplifying this, I get limit as k goes to infinity of k plus 1 factorial over, k factorial over k plus 1 factorial times all of that in absolute value times x, which is equal to just limit as k goes to infinity of 1 over k plus 1 times x. And the limit as k goes to infinity of 1 over k plus 1 is just equal to 0. So this is equal to 0. Oops, sorry, I made a small mistake. It should be x x minus 1 to the k plus 1, x minus 1 to the k, and then here it would just be x minus 1. X minus 1. Right, and this is equal to 0 for all x, right? So there's no x dependence here because the limit, the first part of the limit goes to 0. So therefore, since this limit, so limit as ak plus 1 times x minus 1 to the k plus 1 over ak x minus 1 to the k. Since this limit is equal to 0, which is less than 1, by ratio test, the power series converges for all x, right? Because there's no x dependence in the limit. So if it converges for all x, the radius of convergence is infinity. Convergence is infinity. Okay, so that's that is power series for you. Again, do a few examples from the textbook and the assignments. You'll encounter multiple different scenarios where the radius of convergence is infinity, it converges everywhere, or the radius of convergence is 0, it only converges at the single trivial point, or the radius of convergence is finite, so it converges on the open interval as given in the definition, and it diverges outside that, and then on the radius of convergence it may or may not converge. So again, give all those types of problem a try. I'm going to finish off by talking about Taylor series, which is a special type of power series. All right, so let me definition. Okay, let f be a function. Let f be a function, and suppose that f has derivatives of all orders, with derivatives of all orders at x naught, right? So that just means, i.e., f, the kth derivative of f at x naught exists, right? So we say, or rather, the Taylor series for f, right? So the Taylor series corresponds to the function f at the point x naught is the power series of the form starting at k equals 0 to infinity, f to the power of k, or sorry, not power of k, the kth derivative of f evaluated at x naught over k factorial times x minus x naught to the k, right? Where fk is the kth derivative. Right? So that's the Taylor series, and a Maclaurin series. Maclaurin series of f is the Taylor series centered at, it's a Taylor series at at 0. At 0, right? So in other words, it's of the form f of k, the kth derivative, sorry, evaluated at 0 over k factorial times x to the k. So let's see an example. So example, compute the Maclaurin series. For the function f of x is equal to e to the x. And I'm doing this example because it's a relatively simple example. Most examples won't be this simple. So in this case, the Maclaurin series is equal to, just by looking at the definition, is f of the kth derivative of f evaluated at 0 over k factorial times x to the k. Right. Well, we know that f of 0 of x is just equal to f of x. Like the zeroth derivative, we conventionally say is just the function itself, which is equal to e to the x. Now f, the first derivative, is equal to f prime of x, which is equal to e to the x, and the second derivative is equal to e to the x. The point is all the derivatives are equal to e to the x. Right. So this implies that f of k evaluated at 0 is equal to 1 for all k. And again, this is a fairly simple example because e to the x is its own derivative. Most examples will be more complicated than this. So now if I just plug this in, the Maclaurin series so plug in definition. Right, I get the Maclaurin series for f of x is equal to 1 over k factorial times x to the k. Is Maclaurin series. For e to the x. And this is about as much detail we're going to get into Taylor series and Maclaurin series. And that's everything for today. Thank you for watching. Again, if you have any questions, please post them on Piazza. I do follow regularly, and I'll be happy to answer any questions before the exam.